Yep. Newton again. He returns.
Oh, really?
This time with a vengeance. Sean! We're starting.
Newton.
Did you write this down? Come on, where's your notebook?
I think so. I don't know.
What? Ready? Did you write this down? So what are you thinking? You're thinking, but Stephen, we did Newton's law, didn't we? True, Newton has many laws. This is the next one. Yeah, more than three actually. Yeah, smart guy, you see, smart guy. Okay. So Newton's law. As you know, the Earth pulls other masses to it, and the Sun pulls the planets, such as the Earth, towards it. So there must be some kind of field. Too bright? Yeah, okay. Okay, so as I was saying, there must be some field, like an electric or magnetic field. Although, of course, it's not electric or magnetic, it's something different, around the Earth. So let us suppose that a field, a gravitational field, is around the Earth, and other masses too. It would look something like this. Everything gets pulled towards the Earth. Now, notice that the field points towards the centre of the Earth. And what you can't see in this picture, the field always points into the mass. Unlike a magnetic or electric field, you can't have it coming out, but it can only go in. In other words, for gravity, it can only pull, it can never push. This is a big difference for gravity compared to magnetic or electric fields. It would be pretty nice if we could make gravity fields point the other way, because it means we could have floating cars, floating skateboards, but we can't. We can only make it pull. So what do you need from this slide? You basically need to draw this field, and note it's called a gravitational field. And can you see I've drawn the equipotential lines as well? You see these lines are the equipotential lines. You remember the potential lines? Yeah. So we're missing Bruce, who has a headache. I got his email, and Monica. Not Monica, Chrissy, sorry. Yeah. Chrissy, I know. And look, I haven't eaten my porridge yet. Look, I still have half a porridge to go. This is the problem.
I'm Brian.
He's right there. He's a good student, aren't you?
I always remember Brian.
I forgot about Jerry, actually. Okay, did you draw that? Oh, come on, it's not a work of art. As Bruce would say, this is not an artist class. Got it? Continue? It was discovered by Newton that the masses attract other masses, and the bigger the mass, the more force, and the closer the masses were together, the more force. In fact, Newton found precisely the formula for the force. It's G m1 m2 over r squared, where F is the force, of course, the m1 and the m2 are the masses, and they're separated by a distance of r, and that r is between their centres. G is a constant, 6.67 times 10 to the minus 11, and the units, you could work them out, they're Newton meter squared per kilogram squared. This formula should look kind of familiar. It looks like what formula? Now, remember yesterday I said note the K was big, 8.99 times 10 to the 9, wasn't it?
Yeah.
9.
9.
Yeah.
9.
In this one, note that G is small, 6.67 times 10 to the minus 11. In other words, there's a huge difference in strength for a gravity field and an electric field. In fact, what is it, 10 to the 20 is the difference between the two. This is huge. It means either electric force is very strong or the gravity force is very weak. In fact, it turns out the gravity force is very weak because the other forces in nature are much stronger than gravity. In other words, gravity is the weakest natural force. Extremely weak compared to the others.
Is it that weak?
It's very weak in comparison to how strong the others are. It's all relative, KJ. It's relative to how strong the other ones are. So if you look at the four forces of nature, gravity is way behind the other three in strength. Extremely weak force.
What is like sun's gravity?
But the sun's gravity is only big because the sun is so big. I mean,
Mass, dude.
because the mass is big. But I mean, if you were to try and make a force, an electric force, as strong as the sun's gravity force, you would not need it to be as big as the sun. You might only need it to be, I don't know, as big as a house or something.
Does this work for human?
Yeah, there's a gravity force between all masses.
So we are trying to go closer to the bigger size of.
Yes, but this is so small, you can hardly notice it. You would need very sensitive equipment to notice this, like really, really sensitive equipment to notice it. It's extremely difficult to do in the lab, but it has been done. I think they did something where they hung two large lead spheres of maybe like, I don't know, like a 50 kg each or something, and using a very sensitive equipment they could detect small gravity force between the two. And when I say small, I mean like, I don't know, 10 to the minus 20 or something, you know, tiny, tiny force. Okay, did you write Newton's new formula down? Yeah. Now notice how similar this is to Coulomb's law. We have not said yet what the field strength is. So remember, for a field, electric field, the field strength was force per charge. So if you draw a comparison, if for an electric and a magnetic, for an electric field, the field strength was force per charge, what might the field strength be for a gravitational field, if you kind of compare it? So an electric field is for force per charge. What might it be for a gravitational field? What could it be? Yeah, force per mass is what it is. You sound surprised that you got it right. Are you surprised? So we'll call the letter G. I know that's the same letter as 9.81, but just for a moment we'll call it G, just to represent the field strength. And it's the force per mass. So mathematically, it's just simply F over m. Just like F over Q. Now we'll continue in a moment, but just write this much down to begin with.
Also, gravitational field is by the method of RC G.
Yeah, that's what I'm going to do next. I mean, that's what you can guess the next line is going to be. So, as KJ was saying, can I? No.
Yeah.
Yes. Okay, so here is, say, Earth, and here is a small mass, and that's being pulled towards the center in the gravity field, and the gravitational field strength we said is equal to F over m, which is equal to GM over r squared over m, where the r is this distance. But of course the m's cancel.
Yes.
So you can actually write it like this. GM over r squared. Who's that?
Come in.
Who is it?
Not coming.
Oh, just
Oh.
about. Come on.
1 minute. 16. Yeah.
Why are you so late?
I won't have late.
Why'd you wake up late? Ah, lab report. Were you working on your lab report last night?
Yeah.
Until what time? No, what time? What time?
I finished my lab report.
At what time? 12?
12.
That's not late. I went to bed at 1 o'clock last night.
Me too. I don't want to.
Ah, you're a boy. You need your sleep. I understand.
I don't want to get up.
Yeah. Okay. As you're right, KJ. This is the formula for gravitational field strength around the Earth. If you, or not just the Earth, if you know it's the mass and the radius. So, yeah.
How do you know metaphor? By the way.
That is something we'll actually calculate in a later lesson. There is a way to calculate the mass, and it has something to do with the moon. We'll do an example where we calculate the mass of Mars by actually observing the behavior of its moon. It's quite interesting. But you're right, how exactly do you do it? We will see that in the next lesson, I think. If we put a small mass near a larger mass, we can arrive at this formula. And the units, of course, are newtons per kilogram. This is a useful formula as well. I can't remember. I don't think this one is in the formula book, but I think this one is. I'll have to double check. One of them, maybe both of them are in the formula book.
Did you
Yeah.
go to the pre-physics drawing?
Like, what? This whole thing?
Yeah. What is the big M and the small M?
Simply any large mass that's pulling in a small mass. That's all. Yeah. Continue. I think we can now, actually, yeah. The most important student has arrived. Why do you think I was talking about you?
I'm not saying something.
Oh, well, that's true too. Why did I think you were saying thank you to me? Yeah, no, that's a fair point. Fair point. Okay, continue. Come on, dudes. Oh, stuck. I must have a large picture on the next page. There you go. Okay, so just to recap. All masses produce a gravitational field, and this attracts other masses to it. We only notice this for large masses like the Earth or the Moon or the Sun. The force F, we can find it by using Newton's law here. The reason I use a small m and a big M, we could use M1 and M2, but it's really to remind us that we're usually looking at a big mass and a small mass together. Fields, the gravitational fields always point towards the center of the mass. This was also discovered by Newton.
Sure.
Yeah.
What if the both mass are the same?
That's fine. It's not naturally happening because, see, what happens is if both masses are the same, then it means they have equal force and acceleration. So what will happen is they'll accelerate to each other, and they'll combine and form a larger mass.
So is it force zero?
No, it's not zero. Each has the same force and the same acceleration, so they'll move together. In fact, this is actually important because it means if you have two things with the same mass, they'll come together to form a larger mass. And actually, this is the process to which new planets and stars are formed. So you might actually have, for example, two small stars or two small planets. If they're equal in mass, they'll pull towards each other and form a larger planet or star. So this is how come we have things like Earth and Moon and the Sun, because they were pulled together by smaller things. Then they'll become big enough so that if something small comes along, two things will happen. Either the small thing gets pulled into the large thing, or it enters its orbit. But even as it's in its orbit, it will eventually get pulled in. Or move out. It's not stable. Presently, the Moon is moving outwards as it orbits, and the Earth is moving inwards as it orbits the Sun. So I don't remember, like maybe a kilometre a year or something, the Earth radius is decreasing, spiraling into the Sun. Then that's it.
So things like climatic change really not
No, believe it or not, the distance the Earth is from the Sun, it actually doesn't have what's quite interesting about the Earth is it's able to regulate its temperature to a certain level. Like, believe this or not, the amount of energy from the Sun, changes. Some centuries there's more energy from the Sun, and some centuries there's less energy from the Sun. The difference is up to 10% over the thousands of years. Even though the energy from the Sun has varied up to 10%, the Earth has kept its temperature reasonably constant. So you might say, how can the Earth keep its temperature the same, even though the energy landing on it is changing? I wonder if anybody knows why. Why is it the Earth is quite special in that it's able to keep its temperature roughly the same until humans came along, and other planets can't? What is so special about the Earth that makes it keep its temperature quite constant? No, because there's maybe water and ice on other planets.
Atmosphere.
There's atmosphere on other planets, like.
Between sun.
But the distance changes.
Also,
No.
It's not. It is not too far. Not too close.
Yeah, but the Sun can get hotter or colder, and the temperature on the Earth is still the same. Does anybody know?
because the distance.
Because of human.
Oh, because they're
Closer.
living.
What?
Yeah, correct.
Well, what?
Because there's life on Earth is what keeps the temperature constant. Yes.
Life.
Correct. I'll give you a very, very simple example, okay? Here's a planet. I'll call this planet Planet X. Okay? There are two things that live on this planet. We'll keep it easy. There's white flowers that live on the planet, and then there's black flowers that live on the planet. Just to keep it simple. Now, you'll see why I'm doing this in a moment. Now, the white flowers, they love the heat. When it gets really hot, you get lots of them, okay? They love the heat. The black flowers, though, they don't like the heat. They prefer when it's cold. So you can imagine then that means the black flowers kind of grow on the north and the southern pole, whereas the white flowers would grow around maybe the equator. No, this is a very simple model, okay? Very simple model to give you the idea. Now tell me, what would happen if all of a sudden the sun had 10% more energy? What would happen to the plants here? Which plant would grow and which would decline? The white flowers who like the heat would increase, and they start to move south and they start to move north. And what would happen to the black flowers? They would reduce. But you know from basic physics, maybe from middle school, that white doesn't absorb heat as well as black. So the planet's surface becomes more white. This means the heat reflects outwards, and the planet cools back down. And then what happens to the black plants? Then they grow back. If there's too many black plants, if there's too many black plants, then the planet will start to warm up again. And in this way, a balance can be found to keep the temperature right. Now, this model is extremely simple. It's much more complicated than that when you think about all the different things that live on the planet and all the ways they affect the atmosphere. You know, but like for example, if CO2 increases, then you would have the trees. There should be more trees growing. Which then, what do trees do? They take the CO2. The problem is when you have humans who both increase the CO2 and burn trees, then the balance has been broken. Do you understand?
Yes.
So the planet is capable of keeping itself at the right temperature. It's only a problem when you have a species like humans who both increase the temperature and stop things that reduce the temperature. Hence the problem. I'm going to move on now because you're annoying me. Right. The field around a small mass can be ignored when compared to a bigger mass because it's so weak. And because masses are positive, the fields never point out, but only in. Point in. And the strength can be found using this formula. And this, in fact, we'll see what this is now. Okay, so have a look here. Here's somebody standing on the earth. They have an M, this has an M. According to my formula, we have F equals MA. True? So then A equals F over M. But if they're standing on the surface of the earth, then we know that this is 9.81. Yes? But what is F? That's GMM over the radius of the earth squared, and this is the mass of the earth, over the mass of the person.
Big M is person or
sorry, big M is the earth, small m is the person. Yeah, this is the earth, this is the person. Yeah. What cancels here? This. Now we know what this is. What's this equal to? The field strength, which is G.
G, yeah.
But that's equal to A. In other words, we have the reason I chose G wasn't actually an accident. For the earth, the G is 9.81 newtons per kilogram. And it's not an accident that that is the same as 9.81 meters per second squared. In other words, the field strength can be interpreted as an acceleration caused by the field in this situation here. So for the Earth, Earth's field strength is 9.81 newtons per kilogram. Now, of course, what happens if I am at a height? Is it still 9.81 newtons per kilogram? No, it's reduced because this ore was for the Earth, which is bigger. Yeah. So, in other words, the strength is also an acceleration. And the value of G near the surface of the Earth is still 9.81 newtons per kilogram. Yeah? Okay, so this is just a summary of what we were talking about so far. Okay, so what about the potential energy? When one mass m is trapped in a circular orbit by another mass m, then it will have negative potential energy because it's trapped. And this is the formula. And again, this formula looks similar to the one we did last time. But think really, really hard for a moment. Don't we already have a formula for potential energy when you're in a gravitational field? What is that? Is this MGH? Or is it?
MGH.
Well, it looks quite different. In MGH, the H is on the top. Here, it's in the denominator. It couldn't possibly be the same. Or could it? So, Write this down and we'll have a look at something we can do here with this formula.
But MGH has only one mass.
Yeah. So, let's investigate further.
Teacher,
Mhm.
what do you mean by trap?
You really asking me?
No, I mean,
Yeah.
In
for
orbit.
this case.
In orbit.
So they are always trapped. Right?
No, 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 no. You need to have the right conditions to get something in orbit. What the heck? Oh, that's your skateboard. Well, no, actually, no. I suppose you're right. You said, is it always trapped? Yeah, it's always trapped. We are trapped on the Earth, so we have negative potential energy. Even if I was in orbit, I'm still trapped around the Earth. The only way the Earth is no longer trapping me is if I get far enough away from it that I can't feel its effect. Yeah. So yeah, no, I suppose it is right to say we're always trapped by the Earth. As depressing as that is, yes. Can I continue now? So, what gives? Let's have a look. Here is the Earth, here is a mass, and I increase this mass to a height h and put it here. We said that the potential energy is equal to mgh. Now, just to be really clear, going up or going down, in which direction do I gain potential energy?
Up.
Yeah, if this moves up, I gain potential energy. So just to be a little bit clearer, I'll just say the change in the energy is a plus mgh if I move up. But according to my new formula, the change in the potential energy, or the change in the energy rather, is equal to the energy on the top minus the energy on the bottom, because this energy is bigger than this energy. And we just gave a formula. What was that? Minus GMM over or plus H squared, the top one, minus GMM over or squared.
What is it after?
And by or I call it this. This is or. Oh, sorry. Thank you, Monica. Thank you. No square. Okay. Now, does this look like this? No, it's very different. For example, does this formula have an or in it? A G? A big G? No, and it only has one of the masses, yeah. So let's see if we can simplify this a little bit. What can I take out that's in common? G, M, and M I can take out. And I'm left with 1 over or minus 1 over or plus H. Okay, now, this here, this or plus H and or, this is I need to kind of clean this up a little bit. I'm going to call H equal to minus X. I'm just going to, or rather if you prefer, I'm going to say X equals minus H. So I can just rewrite this a little bit. This is GMM 1 over or minus 1 over or minus X. Okay? And the or is annoying me a little bit here. I'm going to take out that or. So this will be, actually, so perhaps before I do that, sorry, I'll take the or out first before I do that. So what would I have here? That'd be 1 over 1 plus H over or, like that. Now I'll call X equals minus H over or. So I get GMM over or, 1 minus 1 over 1 minus X. Now I don't know if you remember this from math semester 1, but this is actually equal to something. You need to think back to your lesson on long division or sequence and series. It's the infinite series of X. Yep. Now, what cancels here? The ones cancel, don't they? So you're left with minus x squared minus x cubed. Now, etc. Now, is x a big or a small number? And have a look at what I said x is. So is x big or small?
Small.
It would be right to say it's very small. Because normally this h would be something like 2 meters, and the r would be, a few thousand kilometers. Yeah. So in other words, the x is very small. So if x is very small, then x squared is smaller, and x cubed. These are decreasing. Because they're so small, I'll just say this is roughly just that. I'll only care about the first one. The rest are so small. But what is x equal to? We said it's equal to minus, where's it gone? Minus h over r. So this will be minus h over r. So this will equal GMM h over r squared. Yeah. Okay, so let me just rewrite that a bit. That's m here. And here I'll write gm over r squared, and I'll write h here. But what's gm over r squared? Boom! Yes. So, although the formulas look quite different, with the power of maths, I can show you there's no conflict between the formulas. They both work. Yeah? This is a very nice proof. It's actually one of my favorite proofs in physics.
Yes, no.
No. You don't have to know this for the exam.
No, we can't.
But,
That's understandable.
yes, but if you're doing physics next year, you will do this proof. So, you might as well write it down. You are going to do some physics next year, aren't you? Yeah, so there's no harm in writing it down. Because a lot of the students give me feedback when they're at university. They say that their notes from the IFY they found very helpful in first year. Because myself, Lorraine and Colin, we all like to give our students a little bit of, throw in a little bit of what they might do next year just to sort of help them out next year. And anyways, I just said this is my favourite proof, so You like this proof, Sean? Of course you like it. There's another, this isn't true, this is my favourite proof in the IFY, but my favourite proof in physics is Newton's proof that everything gets pulled towards the centre of the Earth. And you might see, does that need a proof? Isn't that obvious? But it's not. The proof to show that everything goes to the centre of the Earth is quite long. It's like 7 pages or something. That's actually a proof too. It is.
What is it for? Is it easy?
No.
It's not.
No.
No.
Yeah.
You must prove it.
All about what?
Yeah, but in a pure maths department, you can't appeal to anything in the real world. You can't say, well, one object and one object makes two objects. It has to be abstract and separate.
Which is math.
I recommend you Google it. The proof is about 100, 200 pages. Yeah. This is what maths people do in maths departments, They have nothing else to do with their time.
Which are they getting paid by
the university? Yeah. Well, if they're lecturers, they're getting paid.
Even though they can't get the result.
Yes, even if they don't get the result.
Wow.
Well, they might not have their contract renewed. Do you know what tenure is?
Yeah.
You know tenure. Tenure means you work for a university forever, and they won't fire you. So it means, Jerry, that even if you don't get results, you can still work there. Yeah, well, you can imagine a lot of professors try to get this status of tenure. It's like their goal. Now, the professor can still get fired if they're being inappropriate or something, but they can't be fired simply because they're not producing results. And the logic behind it is that the professor is free to study what they wish and not have pressure from external bodies to study only certain things. This is the idea. Yeah, like you give the people creative space to pursue their own research, Yeah. But like I said, they won't give you tenure until you're like there for 20 years and you have a good research record, Yeah.
So can I look at the picture?
Yeah. This?
No.
The picture? Oh yeah. It's funny because they found in a survey most people are unhappier after they get tenure, if you can believe that. Because it's kind of strange, but they work really hard and they're motivated, and this drives them to get tenure. So when they get it, it's kind of like, oh, okay, what do I do now? It's a bit like the Wile E. Coyote chasing the Roadrunner. If he actually got the Roadrunner, then would he truly be satisfied in life? What would he do now? This is kind of like it. Okay, you got that written down? It's quite a long proof, but I do like it. It's very nice proof. Yes. Newton's law of gravity gives the size of force between two masses. This force is one of the four forces of nature, which we actually talked about yesterday. And it's also an example of an inverse square law, which we also talked about yesterday. Please note the small value of g. So yesterday I said please note the big value of k, please note the small value of g. It's actually important that gravity, we can see, is much weaker than the Coulomb's law force. Okay, so here's a small example to get started. How much force is there between the Earth and the Moon? And I give you some info. Here is the Earth, here's the Moon, and here is the distance between the Moon and the Earth. So we just have to bash this in on the calculator. Jerry and everybody, could you calculate the force here? That could be the name of this class. The Jerry and everybody class. .67 times 10 to the minus 11. It is on the calculator too, I believe. KJ, does your graphing calculator have physics constants?
Yes, Q.
Oh, great. And it says their names?
Yes.
Sweet. Can I see?
Yeah, up, down.
Ah. Nice. Okay. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times 7.34 times 10 to the 22 over 3,850,000. Pretty big force. What's wrong? Got it? Continue. Right, next one.
That's the answer.
How long does it take the moon to orbit the Earth? Wait, I'll do this one. It's a little bit harder. Now, do you know the mass of the Earth? Yes. Do we know the mass of the moon? Yes. Do we know the distance between them? And do we know the force? We do. We've just worked it out here. So we know the F. And we know it equals, but we also know it equals m omega squared or. So then omega squared, because it's moving in a circle, is F over m or, isn't it? Yeah. So omega is root F over m or. So that means 2 pi over t is root F over m or. So t is, it'll be root m or over f, and then 1 over 2 pi? No, just 2 pi here, isn't it? Yeah. That's it, if I rearrange it.
2 pi divided by.
No, this is right.
Oh, yeah.
Yeah. Now, let's calculate that. So, 2 pi root fraction, and down here is the force, which we just worked out. And which mass do I have here?
Moon.
The moon, which is what, please? And then what's the distance between them? 385 or 384? 385, yeah. 0, 0, 0, 0, 0, 0. Now, what unit will my answer be in? It'll be in seconds. Okay, so let's convert this. This is too big. So this is hours. Like hours, and then we should make it days. So divide by 24.
And we should make it weight.
28 days. But of course, perhaps you knew that. It's about 28 days for a moon cycle.
Huh?
It's about 28 days for a moon cycle. That's why a month is about 30 days. Now, yeah, it's not synced up perfectly. It depends what country you're coming from. So if you're coming from a Muslim country where they use their calendar, their months are more lined up with actual lunar cycles. But for Western countries, our calendar is more around a 1 year cycle. So it means that in the West, spring, summer, winter and autumn are the same time each year. But it means if you're using an Arabic calendar, because they use the moon, it means their dates kind of shift slightly each year.
Yeah.
So like their religious holidays, Ramadan, is not the same day each year for us, So 27 and a half days for the moon to orbit. Okay. Continue? Yep. How much potential energy does a satellite have when it's that much above the surface of the Earth? Okay, so let's calculate that. No. Oh yeah, I should actually say that mgh is only when it's near the surface, because remember we required the distance to be small. Right. Minus g times the mass of the satellite. Oh, did I not give the mass?
100 kg.
Oh yeah, 100 kg. The mass of the Earth, and then the distance, which is 6371000 plus 3578600. What do you think? Big or small number?
Big. Small.
Let us see. Quite a large negative number.
That's Newton, right?
No, this is potential energy, so that's joules. What's after mega? Giga. About a gigajoule. So here, the potential energy is about minus 1 gigajoule. So if you want this satellite to be free, to leave the Earth and to explore space, how much energy do you need to give it? 1 gigajoule. Yeah. It needs to get a gigajoule of energy. Even though it's outside the Earth, it's still trapped by the Earth, and it will need a gigajoule of energy to escape the Earth and explore space.
How much is that?
Gigajoule is a lot, but it's not too bad. But you got to remember, the situation is quite worse, because it needs a gigajoule to explore space when it's in orbit. I never worked out the energy to actually first get it to orbit. So the total energy is huge. It's huge. And you can see this. That's why rockets are so big. Because to get something escaped from the Earth, it requires a huge amount of energy, because the potential energy is so negative. It's so trapped by the Earth. A lot of energy is required to free it. It's a bit like with the electron being freed from the proton. It's the same idea, except it's worse for Earth, because the electron is already in orbit. For Earth, you first have to get it into orbit, then free it. So it's quite a bad situation that way. Okay, so about minus a gigajoule. Yeah? Okay, so I think that's probably it. Yeah. Oh, calm down. They're quite short, as you saw. Monica, these questions are quite short. Don't forget, you have all the information you might need at the bottom, like masses and radius and so on. Oh, you thought that was for a question now. Do you feel a bit better? What's wrong, KJ? Did you skate over dog's poo?
No.
Dog poo is kind of hard to get off, trust me. I've stepped in plenty. What's wrong? What is that? Did you go over some paint?
No. The street was quite wet.
Ah.
And my baby.
Your baby, yeah, it's dirty. You need to clean it. You need to buy cleaning products for it. You can't just use tissue.
Yeah.
It will clean your nose just as well as any other piece of tissue. I don't care if it's from Kenya. Right.